Hi, this is Jason Kendall. Welcome to the next of my introductory astronomy lectures. Today we're going to be talking about the Big Bang. Last time we looked at Edwin Hubble's amazing discoveries and we're going to extend that into the idea of the cosmological redshift. The cosmological redshift is one of the key pillars of the Big Bang and cosmology itself. It demonstrates, just to let the cat out of the bag, that the universe is expanding. So we're going to look at the evidence for that and why we think that we treat that evidence as though it's expanding. Once again, cosmology is the study of the entire universe and everything in it, what it's going to do, how it moves, its origin, and its fate. And next, we are going to utilize an incredibly important principle called the cosmological principle, in that there's nothing special about our location in the universe, other than that's where it's home. And if we see the fact that everything's roughly the same in every direction, maybe not the exact same galaxies, but yet the same kinds of things distributed in the same kinds of ways in any direction, that's isotropy, about any point in the universe, particularly us. And if you combine it with the idea that the laws of physics are the same, meaning there's nothing special about where we're at, then isotropy means isotropy everywhere. If you have isotropy everywhere, then you have homogeneity everywhere and looks the same everywhere and made of the same stuff. That means no matter where you are, you're going to see exactly the same thing, and that will become really important. Okay, so when we look off last time on the great distance debate that was in the early part of the 20th century, it was solved by Hubble in 1929, was the distance between the Milky Way and Andromeda, and trying to find the distances to the spiral nebulae, which puzzled people for a long time. So let's do a quick review about that. A couple of galaxies like M81 and M82, nobody really knew how far away these nebulae were, and they were thought, like especially the one on the left, M81, was thought to be a star-forming region or a planetary-forming region or something like that before people knew that it was 12 or 14 million light years away, and that thing is composed of hundreds of billions of stars. Same with the other one on the right. These are interacting galaxies that are pretty nearby us at about 12 million or so light years away. And the distance, the detection of that distance was a major story about the size of our cosmos. So how do we know how far away they really are? And what we're really going to talk about is the expansion. And in 1912, prior to Hubble's discovery, Vesto Slipher at Lowell Observatory and a few others, mostly Slipher, was able to measure over the course of a few years using getting radial velocities for the spectra of about 25 of these galaxies, which he called spiral nebulae at the time. And he found, of those 25 galaxies, 21 of them show a redshift, and some with very, very, very high speeds, up to 2,000 kilometers per second away. And he said he found that galaxies are rapidly receding, but he didn't have distances. So he knew he was onto something very important, and the discovery and knowing that the significance of the spectra were really, really, really important. He just didn't have distance in order to actually make the connection. But in 1929, Edwin Hubble finally actually measures the distances to a few galaxies, including M31, M33, and some other local group galaxies, and he compared the distances with the recession velocities. He found that the recession velocity gets larger as you get farther. And this was taken to mean that he had found the systematic expansion of the universe. And this is a really, really, really big discovery. In fact, it's probably one of the most important discoveries of 20th century science, without any exception, because it changed the nature, it turned the study of the universe away from stories told in ancient books to being a precision science. And that's where we're at today, almost 100 years later. So how far is the Andromeda from the Milky Way? And that was the question of the 1920s. And what Edwin Hubble did is he knew about Cepheid variables because of Henrietta Leavitt's work, and then refinements by others on that work to actually discover Cepheid variables in, say, the Large Magellanic Cloud, which are a particular kind of variable star. And the variables, Cepheid variables, have a particular light curve that if you find a star with that variability, you found a Cepheid variable. But they also tend to be much, much more luminous than the others. And Cepheid variables are extraordinarily luminous variable stars. So if you can create a good relationship or calibrate the period luminosity relationship, meaning then you can get their distances. Well, that's a good thing. And that's exactly what Hubble did in his work in the 1920s. So he started taking pictures of M31 and M33 and others in order to try to find Cepheid variables, and he did. He found a number of them starting in 1923. And here's another one of his plates from 1926 from the Astrophysical Journal, and you can see he marked up a series of variable stars that he found in there. And so he looked specifically for them and found their periods, and therefore he could derive their luminosities based upon the work of previous people, starting with Leavitt. And what he then did is he followed it up by noting what Vesto Slipher had found, that there are radial velocities. And so he did additional radial velocity measurements with the 100-inch telescope at Mount Wilson, and his work was with Milton Humason. And Humason was actually one of the mule drivers that actually brought the 100-inch mirror all the way up to Mount Wilson in California in order to do that. And he stayed on after his work as a mule driver. I stayed on as a janitor at the place, so he never had any really formal education. But he ended up having a fantastic way with things, and he became one of the greatest observational astronomers of the time. So what he would do is he would work and taking the spectra, and some of these spectra would last between 30 and 50 hours of exposure in order to collect enough light to find a spectrum. And that meant that the same spectrum had to be, because it's photographic, had to be taken out of the telescope every day, put back into the telescope every night, and then done over many, many, many nights, where the object would have to be centered in the telescope and tracked not just by the telescope itself, but by Humason at the observatory. And so this took an extraordinarily long time in order to assemble the light that created the data that you see on the right-hand side. And so they used as to get their velocity data the fact that elliptical galaxies, or at least elliptical galaxies, could be used to this effort, is that the particular kinds of galaxies had certain absorption features, and those certain absorption features were seen to be redshifted. So look at a galaxy, look at a greater and greater and greater distance, it looks physically smaller, it has a greater radial velocity away from us, and that's a very interesting thing. All right, so we see a particular pair of lines, and there's a reference point called H and K, and the H and K lines are the things that they're actually measuring, and we find that they're actually displaced from their laboratory rest wavelength, and that is called redshift. And so when we look at what we really mean by redshift, it's on the top, it's the rest wavelength, meaning if you were right next to the object and took a spectrum of it, the top spectrum is what you would see. However, if the object is receding away from us at some speed, then the entire set of spectral absorption features will be shifted to the right by the same amount, and that is what we call the redshift. So when he did this, he found that there was a relationship between the speed with which it's rushing away, which is a measurement of the redshift, which is the measurement of the redshift, and how far away it is that Hubble derived from Cepheid variables. So this is from his 1929 Proceedings for the National Academy of Sciences, and this is his 1929 data that show that the farther away something is, that's the bottom, the faster it's rushing away. And that's the y-axis, or up and down. And he then further went on a couple years later to publish in Astrophysical Journal even more. And his original data is in the lower left, but he found some other ones that are much further off, up and to the right. And that linear relationship that showed the farther away something is, the faster it's rushing away from us, became a universal thing. And one of the great discoveries of the cosmos. And this was it didn't have to be this way. We have to remember that it didn't have to be this way. The universe didn't have to be expanding. It could have done whatever it wanted to do. But it just so happened that this was the discovery. And we assume there's a lot of things that it tells us about the nature of the entire universe to have that the farther a galaxy is from our location, the faster it's rushing away from us. And that's very interesting. So here's Hubble at his desk with the 100-inch telescope inset there, and we looked at, and here's some of his data showing how he measured the redshift of a particular galaxy, and this is the data that he obtained for his first paper that changed the world. So let's look carefully at Hubble's law. Hubble's law shows that there's a relationship between the recession velocity of a galaxy in kilometers per second and its distance in megaparsecs, or millions of parsecs, and it's related by the Hubble parameter, or the expansion rate. So basically that's a way of saying the velocity equals some number times the distance. So the Hubble parameter is essentially a rate of change of the distance. So the more distant a galaxy, the faster its recession velocity, and it's very hard to measure that, this h0, but currently best accepted things are h0 is roughly about 68 kilometers per second for every million parsecs. So you got to go very, very, very far and see something extraordinarily far so that you can actually start to see this effect. Now we measure what we measure today is roughly between 67 and 69. There was a lot of projects, and one of the most important reasons for the launch of the Hubble Space Telescope was to actually measure, to discover Cepheids and measure the Hubble relationship to great extent. And that's what the Hubble Key project did, and they have a number of things. I provide the link down there at the bottom. And they discovered, I believe their measurement was somewhere around 75. But h0 is extremely hard to measure. It's really hard to measure. Recession speeds are pretty much easy to get because, you just take a spectrum and see how far they get shifted. But the distances are much harder to measure. So making an accurate distance measurement is very difficult. So that's where most of the errors came into account. When I was in grad school in the 90s, the thing about the redshift, or the entire Hubble relation, is nobody could decide between whether it was 50 or 100. Now it's well known to be about 68. So this is very interesting that it's kind of gone right smack in the middle of the extremes. So let's look at what it means to have a redshift. The important thing is it's like a Doppler shift, and what they did is they assumed that the rest wavelength, which is the lambda sub O, or that's the observed wavelength, lambda sub O, and then compare that to the emitted wavelength, lambda sub E. If you do a ratio of that and subtract 1 from it, that's equal to the speed with which it's traveling away or towards us compared to the speed of light. So essentially, you're saying is how much different is it how much different is the observed wavelength from the emitted? If it's not different, then the speed with which it's rushing away will be 0. If it's really different, it can be twice or 3 times or what have you. It can have a very, very, very large redshift. So that's the analogy for it. So what we have now is that we can define redshift, and redshift cosmologically is defined in this way. It doesn't have units like meters or seconds or anything like that because the definition is embedded in it. So I just basically took that previous equation and got rid and combined c divided by v and turned that into z. And so z is the standard way we talk about redshift, and it's simply the difference from the observed to the emitted wavelength divided by what it was when it was emitted. So you can see that if the redshift is 0, then the observed equals the emitted, and that's basically right next to you. But if it's rushing away from you so quickly that the observed wavelength is twice the emitted wavelength, then that would be a redshift of 2. All right, so here we can see a summary of all those things. The speed of the redshift, v redshift, is equal to the speed of light, c, times that redshift value. That's in the middle. And at the top, we see the relationship that I kind of described and put it all together. And where that square rooty sort of thing comes at the top right, is because if you are looking at it relativistically. Now, relativistically means that the recession velocity is nearly the speed of light. And you have to use that equation. But if the speed of light, but if the recession speed is small compared to the speed of light, then it approximates. That's what that double tilde sort of equation, that bendy equation means. Then that equation, then the previous thing with the square roots and the -1 to that gets really, really, really close to v over c. If the v over c, the speed with which it's receding compared to the speed of light, is pretty small. So that equation approximates that. That's what that double tilde means, that double wavy equation. Now what's funny is that when we look at the bottom, is the redshift is approximately, and this is really important, it's approximately related to the time that we observe it in the age of the universe compared to the time that the light was emitted in the age of the universe, times what the parameter, the Hubble parameter for the current value of the Hubble parameter is today. So that means that the redshift is equal to the distance divided by the speed of light times the Hubble parameter today. That's what T sub naught means, is the time today, today's time. And T observed could be just today's time, right? But T emit is when it was observed, when the light was emitted from that galaxy. And when we say a galaxy is like 100 million light years away, T emit is 100 million years ago, and T observed is now. So that gives you a big difference of time to go back in time, and so the redshift can be a large number. All right. For nearby galaxies, therefore, the redshift is proportional to the distance. It does not work for really distant galaxies. The equation changes. But for nearby galaxies, the distance d is approximately, that's what that waggy equation means again, is approximately to the speed of light times the redshift that you measure by looking at the observed and emitted observed wavelengths, and when you know what the emitted should have been, divided by the Hubble constant. Well, measuring the Hubble constant is a real trick, and that is really the trick, and that was what Hubble did in 1929. He actually, that slope of that curve, that line, is the measurement. Now you can see there's a lot of spread around that, and that makes it tricky to measure, and you've seen other things like that too. So, but our most important element that we're going to take away is that all galaxies, only with a tiny number of exceptions, like tiny means a handful, like 5 or 10, are receding away from us. The recession is what we call the cosmological redshift because of the cosmological redshift, it's not a Doppler shift. Why isn't it a Doppler shift? Okay, a Doppler shift means that the galaxy is simply rushing away from us, right? So if you hear a Doppler shift, like a siren going off and there's an ambulance is driving down the street, then that Doppler shift happens because of the relative motion of the ambulance with respect to where you're standing. And okay, that's fine. So then if it's not, but then why can't it be a Doppler shift? Because the cosmological principle says that there's nothing special about where we are in the universe. And if there's nothing special about where we are in the universe, then what's this deal with everything rushing away from us faster and faster and faster as it goes out? It makes us look like we're at the absolute center of something, of everything. But that's not the case. If the cosmological principle is true and everything looks the same in every direction, and we know that the laws of physics, or we can at least posit that the laws of physics are the same everywhere, then it makes no sense for us to see, and we don't look really special. Our galaxy looks pretty much like other galaxies as we've seen. So if our galaxy looks like other galaxies and we're not special, then that redshift measurement is not special. And if the redshift measurement is not special, then it can't be a Doppler shift, meaning that stuff is flying away from us because it's moving, it's got rockets, something else must be doing it. And that something else is the stretching of space-time as the universe itself expands. But the universe drags on the light. And so galaxies don't get stretched by the universe's expansion because gravity holds them together. Protons and electrons don't get stretched because they're little particles of mass. However, light has a definitive wavelength. So as it travels, the universe expands, and that actually extends and makes the light grow because there's nothing, quote, keeping the light from being stretched. So the light gets stretched as it goes through the cosmos. That's where the origin of the redshift is. So the redshift distances have limitations. You can only know the red H0 to a few percent, but that's getting better and better and better with more and more observations of various kinds. So random galaxies, so you can't use redshift for close-in things because then the cosmological expansion is dependent. It can be overwhelmed by, say, the random motions of the galaxies. So if you look at the Virgo cluster of galaxies, you've got random motions of those things that are comparable to the cosmological redshift. So really you need to look at things that are extraordinarily far in order to start really saying, oh, now the dominant motion is the redshift. So you got to get there, you got to get out to the far stuff before you can use it. But as soon as you get out there, then you might as well just call things by their redshift, because now we say that the redshift is there. So we might not, since H0 is not well known, the best way to actually discuss what the distance is actually simply to declare about what the redshift of the object is. All right, so the lower left-hand corner here is Hubble's data, and we can see a Hubble diagram for a different kind of thing, the distance as a function of velocity, recession velocity as a function of distance. And this is for a bunch of type 1a type supernovae that was published in 2004. And we can see that this particular data set shows that the farther you go, the faster it's rushing away from us. That's really what we're talking about. And this is from another group, from Mould et al., who has actually compared various and sundry methods, and they averaged them out to show that it's about 72 kilometers per second per megaparsec. But we see that there's 5 different methods by which people were measuring this number of H0, and they all give pretty good agreement, with the brightest objects being the type 1a supernovae. And we have all sorts of different ways of measuring distance, and somehow they all come up with roughly the same answer, which is fantastic. But the most widely accepted value comes from measurements of from the cosmic microwave background due to the European Space Agency's Planck mission, where H0 is approximately 68 or 67.7 kilometers per second per megaparsec, which is a really accurate measurement compared to what we're seeing in this graph. This graph has a spread between 65 and 79, but the Planck mission has narrowed it down to 67. So this is really interesting. So how do we interpret, and why do we interpret this redshift as the expansion of the cosmos? It's really important to get at that, so let's kind of dig away at it a bit. We do recognize in the world today that yes, there is a cosmological expansion, so exactly what does this come from? Well, first, remember Hubble's law is empirical. It came from observations. He simply fit a line to the observations and found some empirical data, meaning he took data and found a relationship between them. Vesto-Slipher knew that these things had redshifts, but it was until Hubble was able to get the Cepheid distances to these galaxies in order to make this relationship. And every other empirical data point that's ever been found has shown that this is also the case. So it has been found by numerous researchers doing lots of different things from different cultures, different places, different methods, different times, so this is a real thing. So let's see what we mean by the expansion. It is not motion through space. It is not about the galaxies are moving through space. We must think instead that space-time itself is expanding and getting larger. That thing that we call space and time, or space-time, or space, is getting larger. And as it gets larger, galaxies just get kind of carried along. Now, when the universe gets twice as big, the distances between the galaxies are twice as far. And so therefore, the sizes of the galaxies don't change because they're bound together by gravity, and that, remember, overcomes the expansion because the expansion is very small compared to the rest of it. So the space in your room is expanding, but you know what? You have to look at megaparsec size scale, so it really doesn't do too much inside of a room. And in fact, the space between the atoms inside a table or a chair or just inside your head or whatever you like, the electrostatic force overcomes that expansion, so they don't get spread apart. So This is a general expansion, so everybody sees everything. So we can say with confidence that there is no center and all observers seem to be at the center. That's what we mean by this kind of funny thing. So take like kind of a balloon sort of thing and stick a whole bunch of things on the surface of the balloon. And why do we use the balloon analogy? Maybe you've seen this a bunch of times. Why do we use this balloon analogy? Because we take the three-dimensional, or the up, down, backwards, forwards, left, right version of space, and just for visualization purposes, we eliminate, say, up and down. So we only care about left and right. So how would we make left and right work? So you can either take a sheet or a balloon, but people know about balloons. So paint a bunch of dots on the surface of a balloon and imagine that all you can do is go left and right on the surface of the balloon. You can't go into the balloon. You can't go below the balloon. You can't go up above the balloon. You can't go inside the balloon. You can only stay on the surface of the balloon. So if you're only on the surface of the balloon and you start puffing it up, then the things on the surface of the balloon will stay the same size, unless if you paint them, then they'll stretch. But let's say you stick on some stickies, so like a couple of little icon-y sort of stickers. The stickers will simply, on the surface of the balloon, will expand away from each other, but they won't change in size because the stickers don't participate. Now the sticky tape will drag them away from each other. So that in this case, it looks like the robot in the center is seeing everybody expand, but if you look carefully, you'll see that everybody else would also see everybody expanding. And the farther away somebody looks, the greater the distance appears to be. And so everybody would see it, and the nice thing about thinking about the surface of a balloon is just rotate the balloon and look at a different set of stickies. And that sticky then looks like it's in the center as you expand. And then you look at another set of stickies on the same balloon, and you rotate the balloon around and then keep expanding. And that sticky stays in the center. So it doesn't matter which sticky you focus on, it will seem to stay put while the other stickies seem to move away as you inflate the balloon. So this image does not mean that these things are inside the surface. It means they're on the surface of this balloon. And so what we mean by space is that for this example, as we reduce the three dimensions, up, down, backwards, forwards, left, right, to just backwards, forwards, left, right. And we've ignored the third one because, well, that's kind of hard to do. And so let's make an analogy that'll help understand. All right. Now the universe grows, and so the size scales of objects that are not bound together is like something like light. So light is not gravitationally bound to itself. So as the universe expands, it gets stretched too. So the wavelength of light gets stretched as time goes and as light travels through the cosmos. So what's kind of deceptive about this particular image is that waves of light are not standing waves on the surface of the balloon, but you'd have to think that the wave is moving from, say, left to right. And as it moves, the ground, the surface across which it is going is stretched, and because it has a wavelength and it's not pulling back on itself, that wave gets stretched. So that's what explains the cosmological redshift. So we can look at the bottom little graph. We got two little galaxies, and on the right-hand side, the galaxy emits some blue wavelength of light. And that's the distance that they were apart when the light was emitted. So that's what de-emit means. And then there's lambda sub-emit, which shows that it was blue wavelengths of light when the light was emitted and the galaxies were close. Now, as the universe expands, the galaxies spread apart, and the light travels from the place it left towards us, and then we receive it at a new wavelength, which is a longer wavelength. So the universe has stretched by, say, twice or 2.5 times. This looks like 2.5 times. So the wavelength will be 2.5 times greater, and the galaxy will be 2.5 times farther. And that is the distance now and the wavelength now. So the wavelength now compared to the wavelength that was emitted is proportional to, in fact, is exactly equal to the distance now compared to the distance that it was when it was emitted. So the cosmological redshift is simply the fact that the universe is dragging on the light and stretching it as it travels. So the galaxies don't stretch because they're bound together, but light does stretch because it is not bound together. Here's another little graphic that kind of shows that. And another way we can think about it that's really kind of interesting is to think about light travel time. How long, how distant was it, and how much time it took. So the emission distance is on the bottom, and it starts as blue, and when it arrives, the distance now is there. So when we think of something of saying, and then there's like two paths, and the path that's way on the right is the path that the galaxy took after it emitted the light. Remember, light does not travel instantaneously, so when you look at something, you don't see it as it is now, you see it as it was when the light was emitted, because it took time for the signal or the light to get here from there. Now we're just here, so we stay put in time, so time goes from the bottom of this diagram to the top. Now the light itself, the photon, travels through time, and as it travels it gets stretched, and as it gets stretched its wavelength gets longer, and if its wavelength gets longer it gets redder. And so that what we call that travel time is the light travel distance, or the distance in, say, light years. That's what the vertical scale is, and that is what we would call the distance in light years, meaning how far did the thing travel if we presume that we say light speed times the time that it took to travel. So the up-down time, blue arrow, shows the light travel distance. The emission distance is also a valid distance. It says, well, what was the distance when the light was emitted? And the real distance, or the distance now, or called the proper distance, or is if we stop the expansion, just could halt it for a bit, and then walked a whole bunch of meter sticks to the right from our current, from where everything is at the top, and walk all the way out, and we would see exactly how far it is. But remember, the universe is expanding, so that's kind of tough to do. So you have this thing called light travel time distance. And so you have a light travel time distance, which, remember, photons don't have clocks, but they do get redshifted. All right, how does redshift measure expansion? Let's really get to the nitty-gritty. Distance measurements are always some length. So it doesn't matter how that length is measured. But what you can do is you can make, say, paint a big triangle in the universe. And I'm going to color that triangle purple. It's got 3 points and the triangles are there and here. And then we can say, let's start with the triangle when the universe is, say, small or a go. So I'm going to call it having a scale factor of A, and A is the value of the scale factor of how big the triangle is in general. And that's what it is then. So now what I'm going to do is I'm going to expand the triangle. So I expanded the triangle to a scale factor of now. And now its size is twice as big. Every side of the triangle I just made twice as long. And as I made it twice as long, the scale factor is twice as big. So the purple, every side of the triangle, is exactly half the size of the side of the green triangle. I invite you to try this at home. So the green triangle is double the side on each side. So the length of each side is twice the side that it appeared from. So the triangle has been scaled up by a factor of 2, and that's what those A sub now and A sub then indicate. It shows you the relative scale sizes. And I've left that funny thing on the left-hand side, that 1 plus z, which is the redshift. So how do they relate? That's a real big question. So remember, redshift is the wavelength observed times minus the wavelength emitted divided by the wavelength emitted. Remember we said the distance now is compared to the distance then? If you set these two equations together, you get that the size now, which is observed, is equal to the size of the universe now compared to the size of the universe then, the A sub now and A sub then, is exactly equal to the wavelength of light observed divided by the wavelength of light when it was emitted. So this is the measurement of this. The light gets stretched by this expansion, and all we know, we don't care how it got stretched. Maybe it went faster and slower and slower and faster. But for this particular object, when we get that thing, we know what the size scale of the universe is compared to today. So maybe when the light was emitted, the universe was 10 times smaller, or 100 times smaller, or 1,000 times smaller than it is today. So as the universe expands, it was smaller then. So now we simply just say, oh, what is the universe size scale now? Let's just call it 1. How about then? Well, it might have been 10 times smaller. So if the universe is 10 times smaller, then the A then is a tinier number. So A now must be 10 times bigger. So A then might be 0.1, and maybe A then is a million, 1/1,000,000th or something. So light gets stretched because these two equations are linked. They are the same thing. So remember, each length gets doubled, so the wavelength gets doubled, and if the purple lines are the wavelength of light on the sides of the triangle, if one wavelength of light was the length of one of the sides of the triangle, then each wavelength got doubled. And notice the length of the triangles are different. The length of the sides of the triangles themselves are different. So you can have different wavelengths of light. And so you can have these different wavelengths of light, which then gets stretched by exactly the same amount. So all redshifts get stretched by exactly the same amount. So let's look more carefully at it numerically, because let's just do this and see, because we want to relate this to the Hubble constant, the Hubble relationship. So what I've done is I've said, think of each of the points of the triangle as either number 1, number 2, or number 3, and r is the length, r sub 1, 2 is the length of one of the sides of the triangle where we're going from point 1 to point 2 as a function of time. That's what the parenthesis t means. It means it's a function of time. And that's equal to the scale factor and how it's changing with time, a sub a as a function of time. That's what the parentheses mean again. And then we say, well, what was the side of the triangle at some time ago? T sub naught. So you begin it at some time, like the blue side, and then you grow it by some scale factor, a sub t, maybe twice as big, and you end up with r sub 1, 2 of the time. So you take length of 1 and 2, r sub 1, 2 at the initial time, t sub 0, and you call that length 1. And let's say you make the scale factor twice as big, just like the triangle below. That's a sub t. After a few seconds, a sub t is now twice as big, or maybe a few hours, or maybe a few years, or maybe a few milliseconds. That's interesting. How fast does a go with time? And then you get to the size scale. So notice what I just did there. I said that a varies with time, but how does a vary with time? That's important. And that's our next step, is that we say the velocity of the speed of the growth of the triangle, v sub, I'm just going to focus on one of the sides, say the hypotenuse. So so let's call the hypotenuse v1 is the longest side of the triangle, away from the right the right angle. So now the speed with which the v12, or the longest side of the triangle, is growing as a function of time is, well, that d by dt, dr12 dt means is the derivative of the speed, the rate of change of the size with time. That's what that equation means. That dr dt thing simply means how does the length of that side of that triangle change with time. Now, but remember, the initial side is a constant. So that means that from the previous equation, we just take the derivative of the scale factor, and that's what that dot means, because I don't want to write out that ddt stuff. So I'm using a shorthand notation. And so a dot of t means the rate of change of a, the scale factor, as a function of time, meaning how fast does it change? We know that it changes, maybe it gets twice as big. But how fast over what time period does it change? Does it get twice as big in 1 hour, twice as big in 1 year, twice as big in a millisecond? So we can then say, oh, but wait a second, we remember that old thing, because r12 is equal to the reciprocal of the scale factor times the function of the radius with respect to time. But wait a second, that's our Hubble relationship. If we look at the left-hand side of the equation, v1, it's just speed, is equal to some crazy number, a dot over a, which is the rate of change of the scale factor compared to the scale factor times a distance, r12. So the velocity with which that speed is changing over time is equal to the speed at the velocity at a given time is equal to some ratio times the size of the thing at a certain time. So if we go forward, we find that that's exactly what the Hubble relationship is. Now I'm just going to take that equation, what I just said before, and put it together. The speed with which one of the sides of the triangle is growing, v12 as a function of time, is equal to some ratio. How the scale factor is changing with time compared to the scale factor times the size, r12, as at a given time. And that's just the Hubble relationship. That is exactly the Hubble relationship because it is a velocity is equal to the Hubble parameter times the time. And so we could drop the parenthesis t if we really want to, and we get the original equation, which is the Hubble equation, which is the velocity that is receding away from us is equal to the Hubble parameter times the distance at which it's going. But notice what we've done with this. We've said that now the Hubble parameter can be a function of time. And we know that the velocity with this recession speed must be a function of time, and the distance that it's going also must be a function of time. So we're allowing for the Hubble constant to not be a constant. Right now, if you look very close, it looks like a linear relationship that's constant. But the farther back in time you look, that number will change. And so we call h as a function of time is the Hubble parameter. And now we see that the velocity is related to the redshift. And the redshift is some measurable that we get. So all we have to do is get some distance measurement. We can get the speed or the redshift speed, the v, from the redshift. And then we can, in theory, measure the Hubble parameter. And that's what those other graphs were talking about. And this is why we say that the Hubble parameter is a measure of the rate of change of the universe's expansion. That's what we mean by it. This is all these bunch of linked equations, and these are the 4 equations that are used to link things together that show that the universe's size scale is expanding. On the bottom, we have the definition of redshift, which shows how the wavelength of light changes from its time of emission to its time of observation. And that's related to the size scale of an object as it's growing. But the middle equation, v redshift, shows how the speed is related to the redshift, the speed of recession is related to the redshift, and the scale factor definition of the redshift falls in so that we can actually relate the Hubble parameter directly to the redshift. All right. What this all means is that the cosmological redshift is exactly the stretching of space-time itself. We do not have to say that the galaxy is flying away from us because it's got rockets on it or something, because that would be weird, because all those things would have had to have been given rockets here, and the farther away they get, the faster those rockets would have to be pushing so that they would get away even further. Now, that would mean that we would be in a really, really, really special place. The place where everybody started. That is not true. We are not at the center of the expansion. So therefore, the cosmological redshift means that the space-time itself must be stretching. What's fun about this is that it also gives us an age, gives us a rough age, because the Hubble relationship shows a relationship between a speed and a distance, so that means it's roughly a time. And if the h0 is about 70 kilometers per megaparsec, we can simply take the reciprocal of that, multiply all the conversion factors out. There's so many astronomical units in a megaparsec, and so many kilometers in an astronomical units, and so many seconds in a year. And so multiplying all these numbers out and dividing up and down gives us that the age of the universe is approximately 14 billion years. Just by discovering what the inverse of the Hubble constant is today, we get a good guess as to what the age of the universe is. That's really interesting, isn't it? Well, what is the exact age? Of course, we talked about this last time, but the WMAP probe in 2012 said it's about 69 plus or minus 32 kilometers per second per megaparsec. The Planck team gave 67.7, and Sloan Digital Sky Survey gives about 67.6. The Holy Cow group, looking at gravitational lensed objects, found a higher value, and they're extremely good data. But that's an interesting thing that there's some tension there that people really think will get worked out. In any event, when you measure the distances, all those distances show that the farther away you are, the faster things are rushing back, and you're also looking farther and farther and farther back in time. But it doesn't mean that is the recession velocity gets faster and faster and faster, and it gets closer and closer and closer to the speed of, well, you can get it so that the recession speed apparently it gets closer and closer to the speed of light, then that the distance actually kind of peaks out. And that peaking out means that's our cosmic horizon. So you can't see anything farther away, more specifically farther back in time, than there has been time for that light to get here from there. And so the farthest thing back in time that we can see is approximately 13.7 billion years. And its current present distance would be much greater because, well, remember, present distance is what we call proper distance, and proper distance is stop the expansion, pretend you can stop the expansion, just pretend for a second you could stop it, put down a whole bunch of yardsticks all the way out to that far thing, and you'd find it's really, 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 really far. However, if you had some way of just saying, oh, we know how far the light's been traveling, and that looks like it's 13 billion light years away. So that's kind of a misnomer. Something that is seen to be at 13 billion light years away is really a bad way of talking about it. What we mean is that the light has been traveling for 13 billion years. That doesn't mean that it's 13 billion light years away. Remember, there's expansion of the cosmos. So if the light's been traveling for 13 billion years, that's just how long the light's been traveling. Right now, that thing is much, 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 much further away. And according to this little graph, it's about 30 billion light years away. So there are things that we see now that are currently so far away that any light that is being emitted by them will never reach us, because the expansion of the universe makes it so that will expand the light away before it can actually get to us. Interesting. So our universe then is expanding, and we measure its distance. We measure the distance of the objects by looking at their expansion rate. And so from Stefan's quintet, we can see that there are 4 galaxies here, and well, 5 actually, but we see that 4 of the galaxies, according to this Hubble image, are approximately 6,000 or 6,500 or 6,600 kilometers per second recession velocity. But then the little spiral in the upper left has only a recession velocity of 800 kilometers per second. Because of the expansion rate of the cosmos, we now know that the 4 yellowish distant galaxies are maybe 10 times more distant than the little spiral galaxy, which looks blue. So all 5 of these are not interacting. NGC 7320 is close compared to the other 4 in the background. So that's interesting that that one just happens to be in the same direction as the others. And you also don't see any tidal interactions between the 4 yellow ones and the one and the spiral galaxy, which looks, relatively speaking, undistorted. Why? It's 10 times closer than the 4 behind it, which means the ones that are 10 times closer, that means it's a small galaxy compared to the ones behind it, because they look about the same size, but yet the ones behind it are much, much, much further. Fascinating. Now, another interesting factoid is that as you look back in time, then if there's an interesting bit that since the universe was smaller ago and everything was closer together, the light the objects, if you look farther and farther and farther back in time, meaning greater and greater and greater redshift, you'll be seeing it when things were closer and closer and closer together. Now, if every galaxy was 30,000 light years across, just presume it for a second, so it's a standard ruler, then as you look back, as you look further and further out in space, things look smaller because they're farther. But at some point, because of the expansion rate of the universe catches up with that look back, we're actually seeing the galaxy be bigger in the sky. So the greater and greater and greater redshift objects would actually look larger and larger and larger, and would look about the same size as something that has a redshift of maybe even a much smaller redshift, a redshift of less than 2. So if we can find a galaxy at redshift of 10, say, and it may very well have the same angular size, and they're both 30,000 light year galaxies, one at redshift 10 and one at redshift 0.5, then, or redshift 1/4, then we know that the one at redshift 1/4 is very near, and we know the one at redshift 10 is very far, but yet they'll have the same appearance in a photographic picture. They will look the same size, if they're the same size. If they're the same size, meaning they're both 30,000 light years across. The fact that we don't see that means that galaxies in the deep, deep, deep past at extraordinarily high redshift are actually much smaller. That's interesting. All right, the universe is expanding. We look like we're at the center, but that's what every other observer sees too. That's the cosmological principle. So if that's what we see, and the laws of the universe are the same for everyone, and our galaxy is no different from any other galaxy, meaning we're not at the center of some grand explosion, we're not sending all these galaxies off into space and things are spinning off, if that's not the case, then every other galaxy will see the same property. Therefore, it's a universal property. The only way for everyone to see the expansion in the universe is for it to be homogeneous and isotropic around the entire cosmos, and so therefore the universe itself is expanding. And that is the discovery of the expansion right there. So the universe today is pretty low density, it's dark and rather cool, and it's still expanding. If you go back in time, 13.772 billion years ago, the universe was very small, very dense, and very hot. The universe was filled with light, and how far back can we possibly go? But when we go back and back and back, we get to the point where it must be hotter. Why? Things are closer together. Higher density. Higher density, according to the ideal gas law, means hotter. Higher density, higher pressure, higher temperature, everything. So that's why it's called a Big Bang or a primeval fireball. But where did this happen? There was no special place. There's no shock wave, there's no expansion front to the explosion, so there was no real explosion. But remember, everyone sees the same thing no matter where you are in the cosmos. Therefore, it happened everywhere, all at once. So the Big Bang is an event in time over all of space, not an event in one place in space at a point in time. No, it is a thing that happened to all of space at the same time. That's what we mean by the Big Bang. It wasn't this little place in space did this thing. No, the thing that we call space, all of that thing, all of those things participated in this Big Bang at that time. And now we measure the rate of expansion of the cosmos by measuring the Hubble parameter. That's why Hubble's discovery was so incredible in 1929, because it leads to this amazing, amazing, amazing conclusion that once upon a time, 13.7 billion years ago, that the universe was tiny, hot, small, condensed, and we have evidence for that because the universe is expanding now, which is really quite amazing. All right, so here's some stuff for you to go over, some review questions, and enjoy that and mull this over because, gosh, this is just the beginning of our study of cosmology, and we'll see you soon.